Swayam Prabha. Digital India. Educated India.
Today we will start our discussions on this software Gromacs, which allows us to do molecular dynamic simulations for a variety of systems. So before we start, let me summarize what we have done so far. First, we started with basics of computer programming, then discussed several numerical analysis methods like interpolation, roots of equations, matrices, solving differential equations, and so on. That gave you an idea of how to write program statements for all these issues. Then we took up a very nice software, Scilab, in which all these numerical methods can be done almost instantly. So it's an extremely powerful software. So you have seen how to execute things using your own programs, which is your ./a.out. In Scilab, we have a Scilab environment, which is really a program that is running. So now we want to do molecular dynamic simulations. These simulations involve a large number of molecules of the order of 100 to 1000. Then since you can have different types of molecules, so the input data from all these systems are different. So therefore the software has to cater to a variety of possibilities. So therefore rather than just one command ./a.out, you will have to do several operations so that your data set is ready. And so today we will discuss all the kinds of data sets, all the kinds of commands, and finally we will also see how to install Gromacs. So my student and colleague Sonunki Keshri, who has been working on this problem for many years, she will give us the detailed information about all this software. Now we will ask her to start introducing about the molecular dynamic simulation on liquid argon using Gromacs software.
So to perform molecular dynamic simulations of liquid argon or any other molecule, there are 4 basic input files that is required. So the first file that is required is the molecular structure, which is in format of GRO or PDB file. That is the structure file of the molecule. PDB is the protein data bank file, so which is easily available from protein RSCB site, and we can as well create a PDB file also. And the Gromacs input structure for PDB file is the GRO file, which we have to convert. The second file which is required in Gromacs for MD simulation is the topology file, which contains the complete description of all the interactions in your system. Basically, it contains the force field parameter like the Lennard-Jones potential, sigma, epsilon, charge, and all. The third file that is required is the molecular dynamics parameter file, that is the MDP file, which contains information about the molecular dynamics simulation itself. That is, it contains the information about which is the algorithm which is required to simulate, or which is required to integrate the Newton's equation of motion, the total number of steps, what is the temperature, what is the pressure that is required, or what is the type of cutoff we are using, and all this stuff. And the fourth file that is required is the ITP file, which is the include topology file, it stands for, and in that we write all the force field parameters, all the detailed information is given in the ITP file.
So can you comment on advantages of putting data in different files like that?
Yeah, because we cannot put all the file in all the like PDB top and MDP file in one single file. If you have different file, it is easier for a user to understand each and every file in detail. Like if you have a separate GRO file, we can know that what this file do, this file contains and all, then what is the information that is contained in a topology file. And if we combine it together, it will be a huge file, and then the user...
And also, don't you think that since these files are separate, I can always change parameters in these files and then make my starting...
Yeah, definitely.
Correct? So,
because anyways,
keeping it in this different modular format allows user to change the parameters their own way. So they can have their own parameters other than what are given by the standard
because anyways
force
all
fields.
these parameters we have to change according to each and every molecule.
Right.
They will have different parameters. So
Okay.
all these are user defined.
Okay. Yeah.
So we have to
please
change
go
it.
ahead. So you have basically PDB, top, MDP and ITP file.
Yes.
Okay.
These are the 4 input file that is
Yeah.
required.
Okay.
So now to perform an MD simulation, we have to have an initial configuration of the molecule of which MD simulation is to be performed. And to generate initial configuration, we use a software PackMol. It is also a free software.
And one of the things I want to say that everything that we are using here are all free software, freely available, so that you don't have to pay anything, no license fees, and these are very, very good softwares. In fact, Scilab that we discussed, they are using the Scilab software even to launch satellites. Launching a satellite is much more than doing a simple simulation in a lab. The simulation can break down, but if a satellite breaks down, it will be a loss of huge amount of money. So many of these softwares are really top world-class software. So we should feel good that several groups in the world are really putting efforts so that all these softwares are available to the public. Okay, yeah. So now we are discussing how to generate initial configurations using a software PackMol. Yeah.
So from PackMol, the configuration which we will get, the format will be in a PDB format, that is the protein data bank format. And so to first we have to log into our remote server, and then we have to go to the PackMol directory using the command cd. So if you type cd PackMol, it will go to your directory PackMol, and we can type ls to view all the files that are present in the PackMol directory.
So you mean to say all these files now they are all from PackMol directory?
Yeah, when we install PackMol, these
Okay.
are all the files that are already present in PackMol.
Okay.
So there are 2 files that we have put in. First is the argon.pdb file, which is the PDB file of liquid argon. So we can open the file using vi command.
So now we want to start with liquid argon because argon is one of the simplest fluids. Something like water or CO2 or any molecular liquid will have several atoms in a molecule, whereas argon is just a single atom. So if you have say 100 or 200 argon atoms, you just have to specify the coordinates of those 100 atoms. So atom simulation is far easier than molecule simulation. So we are starting with argon so that you get a good feel for this. Now lower part is the structure of the PDB file.
Yeah, this is the
Okay.
structure of the PDB file. So I'll give the detail of the PDB file
Right.
in my next slide.
Okay.
So this is the PDB file of liquid argon. So here we have given that in column 1 to 6, it represents the record name of the atom. Right, from column 7 to 11, it's the integer, that is a serial number of atom. Since it is a monoatomic molecule, so there is only one atom, like
Correct.
argon. So there is the serial number, there will be only one. But if you have water or CO2, then it will have oxygen, and 2 hydrogen sites. So there will be 3 separate lines for each atom. And column 13 to 16 is the atom name for each molecule. Since here we are dealing with liquid argon, so the atom name is AR, that is argon.
So you mean to say that AR which is typed on the left side, it can be anywhere between 13 and 16?
Yeah, it can be anywhere
So
between
you
13
need
and
not
16.
exactly start with 13, it can be 14
14
and 15.
or 15 or so.
Okay.
But it has to be in between 13 and 16.
Okay.
17th is the character, which is the alternate location indicator. Then 18 to 20 is the residue name. Since here it is just a monoatomic molecule, so here we'll have argon as the residue name. It is user specified. User can change the residue name according to their convenience. So when we will deal with the water or CO2 or methanol molecules, then we'll have a different residue name. For water we will have say SOL as the residue name, and then the atom name will be different from the residue name for a polyatomic molecule.
So like residue will be H, O, things like that?
Exactly.
There will be
And
3 residues for water, maybe
no,
5
no,
for,
no.
no?
There will be atom name for water. The residue name will be the same. The residue name is solvent.
Okay.
Or methanol in case of methanol it will be MEOH.
Okay.
And there are 3 sites in methanol. One is CH3, one is oxygen, and one is hydrogen.
Okay.
So the atom name will be different, but the residue name will be the same. It has
Okay.
to be the same throughout.
Okay. So residue is like more like solute and solvent.
Yeah, it is more like solute and
Okay.
solvent, and it has to be for solvent, there
Okay.
has to be only one residue name.
Okay.
Or for solute, there has to be one residue name. It cannot have different residue name for each and every site.
Okay.
Then column 23 to 26 is the integer, which is the residue sequence number. Since here it is only one monoatomic molecule, so the sequence number is 1.
Okay.
Then column 31 to 38 is real type data, and it's a coordinate for x-axis in angstrom. Similarly, column 39 to 46 is the coordinates for y-axis in angstrom, and 47 to 54 is a coordinate for z-axis in angstrom.
So now you are saying that all these coordinates are given in angstroms.
Yes,
But in PDB format.
Yes.
But Gromacs needs it in nanometers, isn't it?
Yeah, it needs it in nanometers.
At some stage you have to convert.
Yeah, when we'll convert this PDB file into a GRO file in Gromacs,
Okay.
then we'll convert it into nanometer.
So now these coordinates are given as 0, 0, 0.
Yes.
Instead, can it be like 2, 2, 2? Is
Yeah,
that
it can
allowed?
be. Yeah, it is allowed. It can be 2, 2, 2
So I can
as
give
well.
it can be any coordinate x, y, z.
Yeah, it can be any coordinate x, y, z. Since it's a monoatomic molecule,
Correct.
you can define it according to your convenience.
Yeah, and since our simulation boxes are of the size of say 30 to 40 angstroms, we expect these coordinates to be between 0 and 40. Is that
Yes.
correct?
Yes.
So I cannot give more than the length of the box.
No.
Okay. Yeah. So this 0, 0, 0 could be 1, 1, 1, 4, 5, 7, any combination
Yeah,
of
any combination.
less than the box length
Less
in
than
x
the
and
box
y.
length, yes.
Okay. Yeah. Go to the next one.
Okay. So now to generate initial configuration using PACMOL, we have to have an INP file where we will specify the box length of the, or which kind of box we are going to use in simulation, and what is the coordinate of the box, how many molecules of liquid argon has to be there, what is the name of the output file, and all stuff.
So even if there is no INP file to begin with, you can create a new file argon.inp
we
using
can
the
create
VI
a we can download it in the PACMOL site.
Okay.
There are examples given there, and which is freely available, and you can download it. There they have commented each and every line, like which line stands for what. So you have to have this INP file,
So,
which you can
no,
get.
this INP, is it in PACMOL or created
No.
by the user?
It is created by the user. It is
Okay.
not in the PACMOL file.
Okay.
And so this is the format
Okay.
of an INP file. So here the tolerance which is given as 3.0, it is the distance between two atoms that will be at least 3 angstrom. This is defined by the user. It can be 2, 3, 4 according to the size of the molecule.
So what you are saying is that I have defined one coordinate using 0, 0, 0.
Yes.
Now for liquid simulation, I have to generate a large number of coordinates.
Yes.
So to generate many coordinates, I need to make sure that the second atom is further from the first atom by a certain distance.
Yeah,
That is this tolerance.
Yes, otherwise it will crash the simulation.
Correct. And we may have already discussed what is a Lennard-Jones potential. In that potential, there is a size parameter called sigma. So typically, tolerance should be of the order of sigma or larger.
Yes,
Okay.
depending on the size of the atom or molecule.
Right.
Then there is file type PDB, because in PACMOL we are using the PDB file format.
Okay.
And then there is output liquid argon.pdb. It is user defined. User can give any name according to their convenience, according to the name, like simulation they are performing.
But this file type .pdb, this is not there in your INP file.
This is there in the INP file. File type PDB. It means that the file
That's
type.
the second statement?
Yeah, there is
Okay.
a second statement. What it means is that the input file which we are providing, like argon.pdb, it is in the
Okay.
format of PDB.
Okay.
And the output which we will get, it is in the format of a PDB file.
Okay.
So it is the file type of input and output file, which is a
Okay.
PDB file.
Right.
And then output is liquid argon.pdb. It is the name of the output file.
Okay.
User can change it according to their convenience or the molecule which they are going to simulate. Since here
Okay.
we are simulating liquid argon, so I have given the file name as liquid argon.pdb.
Okay.
And then there is structure argon.pdb. It is the name of the PDB file that we are using. Then there is number 567. That is the total number of argon molecule in the simulation box. And what is meant by inside cube 0.0.0.30 is that it is a cubical box of length 30 angstrom in XYZ axis. And instead the keyword 0.0.0.30.0, we can as well use 0.0.0.30.30.30 to specify each X, Y and Z axis. And then you have to end this file using the command end structure.
So what does this structure mean there?
Structure is the input file that you are providing, that is
Okay.
argon.pdb. When you will simulate water then you have to use water.pdb or
Okay.
the PDB file of water molecule or the PDB file of the
Okay.
molecule which you are going to simulate.
Okay.
Here we are doing simulation of liquid argon, so we have to provide the PDB file of argon molecule.
So maybe the software knows that when you say structure ar.pdb, it starts that file containing all the coordinates,
Yes.
it generates all the 567,
Yes.
then it ends that. Probably, is that the possibility?
Yes, it will
Okay.
go to the argon.pdb file, then
Right.
it will take another, since we are giving here 567
Right.
molecule,
Yeah.
so it will take another argon molecule, and the distance between them will be minimum 3 angstrom since we have specified it, and then it will fill the box of fill the cubical box of 30 angstrom by 567 molecules.
So I think for the learners, you have seen now that there are 567 atoms in a box of size 30 by 30 by 30. So using this 567, you can find out what is the mass of these 567 atoms, and this much mass is contained in a box of 30 by 30 by 30. Take density, that density is mass by volume. Do this mass by volume and see whether the number you get corresponds to density of liquid argon. So you have chosen 567 so that you get the density of liquid argon correctly, which is say around
1.39 grams per cc.
Right. So you please check that this gives you the correct density of liquid argon, because if the density is wrong, all your simulations will be wrong. So the first thing when you do any simulation, you should identify the number of molecules in your box. We have chosen 30 because it's a good number. So even 25 would be good, 35 would be good. But suppose you use 100 by 100 by 100, just calculate how many argon atoms you will have. And the argon atoms will be so many that you will not finish the simulation in several days. Is that right?
Yeah, it's right.
Okay,
It
so-
depends on the box length and number
Correct.
of molecules as well.
So nowadays typical box, see about 50 years ago or 30 years ago, we would use box length of 15 or 20 angstroms. Today 30 and 40 is common. Maybe after another 10 years, they may all be using 100 angstrom because your computers are much faster and more memory is available.
Even 70 angstrom box people have used.
Okay, right. Okay, yeah, please go ahead.
So now to execute the file argon.inp, we have to just type the command /pacmol space argon.inp and then enter. So this is the command that we have to use to execute the file and to get the output liquid argon.pdb. And then after performing it, it will display something like this in the screen, that success, and it's built in this much time is used to build the file liquid argon.pdb.
So this is the result of your execution?
Yeah,
What
this
is
is
shown
the,
below?
Yeah, this is the result of my execution.
So how many lines will be there?
In liquid argon.pdb and the output file,
Yeah.
the output file will have, so to open the output file,
Right,
we will use
okay.
vi command,
Okay.
and this will be the output file. Since we have taken 567 argon molecule atoms, so it will have 567 argon atoms in the liquid argon.pdb file. Here I have just shown 1 to 14, and the last 3 columns are the coordinates of x, y and z axis in angstrom, and it will similarly have more 560 lines.
Total 567.
Total 567 lines, since we have 567
Right. And
atoms.
you should all see that none of the coordinates is more than 30, 30, 30. Right? That means all these atoms are inside that cubic box. Is that correct?
Yeah,
Okay.
because the box length is 30 angstrom, so it cannot have coordinates more than
Correct.
30.
Now suppose for this box size 30 by 30 by 30, I had given 6,000 atoms rather than 567. What will the program execute properly?
No, the program will not execute properly, and it will crash the simulation. It
Because
won't
you
even
cannot
give-
fit, you
Yeah,
cannot fit so many in this small box.
Yeah, it
Okay.
will explode.
Right. So it is like putting 1,000 people in a classroom of 100 seats.
Exactly.
Okay. So now we have a PDB file for the liquid argon.
Yes, now we have a PDB file, which is the
Okay.
first input file which is required.
Right.
So now we will take this PDB file and we'll convert it to GRO file, because in Gromacs, the input file which is taken in Gromacs is the .gro file and not the .pdb file. So first we'll create a directory using the command mkdir. Since we are simulating liquid argon, so we'll create a directory mkdir argon. Now we'll copy the liquid argon.pdb file from pacmol directory to argon directory using the command cp liquid argon.pdb to the directory argon. So we'll use this command.
So what do those two dots mean? Does it mean it goes to a higher directory or a...
The two dot mean that it is going out from the directory pacmol,
Right.
and then it is going to the directory argon.
Right. So the directory argon is at the same level as the pacmol?
Yeah.
Huh? Okay.
So now to convert the PDB file into a GRO file, we'll type the following command, Gromacs command, that is genbox. So if we type genbox space -h, so we can know that what this command does. -h, it stands for help. It will display several things where it shows that which is the input file that is required, which is the output file that we need, and it will give detail of the command.
So
and
that
how
means
it
whatever
works.
that gen box does, there will be many options, isn't it?
Yeah, that there will be many options
So
of
all those will be shown.
All
So okay, so what we will do today, we are going to describe all the commands, and after 1 or 2 days when all the commands are described, we will actually execute it on the computer, so that you would have heard all the details and then you will actually execute, so that whatever is said you will actually see in real life. Okay?
So then we'll type the command genbox space -p liquid argon.pdb, which is the PDB format we have got from pacmol.
Right.
Then -o conf.gro. -o stands for output file, and conf.gro is the configuration file, conf.gro. Then -box 3.0 space 3.0 space 3.0. -box is the box, cubicle box, and 3.0 3.0
It's in
3.0
nanometers?
it's in nanometers. Since
Okay.
in pacmol we have used 30 angstrom, so here in Gromacs all the distance, the unit of distance is in nanometer. The energy units will be in kilojoule per mole.
So earlier we had 30, 30, 30.
Yes,
Now we have 3, 3, 3.
that is in nanometer.
Right. Can this be instead of 3, 3.3,
Yeah,
or will it give an error?
it won't give an error. It
Ah.
can be 3.3.
But it cannot be less than 3.
No, it cannot be less than 3.
Okay. So if you instead of 3, suppose it is 3.5, then there will be more space than what is required for the current density.
Exactly.
So you will do a simulation at a lower density than what you started with.
Exactly.
But if you do 2.5, it will give an error because it is not fitting in.
It is not fitting in, and there might be some argon atoms which will have coordinates of 2.5.
Okay.
Maybe because the box length we have given is 30 angstrom.
Okay.
So some of them may have coordinates 2.5, 2.6.
Right.
So it will not
Okay.
take.
Okay. Fine. So,
So
now
it
we
can
have
be maximum the box length or greater than that.
Okay.
The box length.
Right. Now you have got a GRO file.
Yes.
Okay. So what is the next step?
So we have got the GRO file.
Hmm.
Now if we can view the GRO file using the command vi.
Okay.
It will show the coordinates of argon atom in nanometer.
Right.
Then we'll need a topology file which will contain the force field parameters.
Okay.
That is the Leonard-Jones parameters, sigma, epsilon, charge, mass.
So all these are from the Gromacs force field?
No, these are from OPLS force field.
Okay.
And OPLS force field, when we install Gromacs,
Ah.
there is a top folder that is installed automatically after successful installation of Gromacs. And in that top folder, we'll have all the force field parameters, sigma, Leonard-Jones parameters, sigma, epsilon, charge. There'll be a file, a folder of each and every force field parameters. Like for OPLS force field, there is a separate directory.
Okay.
Then for amber force field, there is a directory. For charm force field, there is a directory. For Gromos, there is directory.
So now suppose I am using OPLS force field,
Yes.
and after some time I decide to use charm force field.
Okay.
So what do I have to do for that?
So you just go to charm. There will be in the top folder.
Okay.
You will have all these directories. So you just go to charm directory.
Okay.
There you will have ff bonded.itp and ff non-bonded.itp file.
Okay.
And since in all like if we use OPLS force field, we'll have a different set of parameters.
Okay.
If we go to charm force field, we'll have some other set of parameters.
Okay.
Right, so we just have to change the parameters. We just have to change the charge, sigma or epsilon values.
So you don't have to reinstall if you have to use different
No.
force fields.
No, we don't have to reinstall it. We just
Okay.
have to change the parameters.
Okay.
We just have to go to the specific directory.
Yeah.
We just have to see what is the sigma or epsilon value in OPLS force field and in charm force field, and we have to change it accordingly.
Okay. Okay.
So
And
now,
if we knew those parameters ourselves, we can change by hand also
Yeah.
in that PDB file.
no, it has to be done in the topology file.
Okay, yeah.
So it is user specified. User can change it according to the force field they are
Okay.
using.
So this topology file is a normal file, not a binary file.
No, it's a normal file. It
Okay.
can be viewed using the VI command.
So which are the binary files in?
The binary file which will be created after we run the energy minimization command or
okay.
MD run, which will come later.
So what is the extension of that binary?
It is the extension is TPR.
Okay. So other than TPR, are all other files normal text files?
TPR and TRR are the binary files which
Okay.
can be viewed using a different command,
Okay.
not by
Not
using
the VI
simple.
command.
Yeah, not the
Okay.
VI command.
Yeah.
So you can open the topology file using VI command.
Okay.
So this is the topology file of argon atom. So here we'll see that there is a NB function defined, which is defined as 1. So non-bonded NB function
So
stands
is that
for,
semicolon for a comment?
yeah, the semicolon is for comment.
So which means the first 3 lines on the left are all comments?
Yeah, the first 3 lines
Okay.
are comment.
Okay.
So where is the default, it's written, and below default there is NB function.
Okay.
NB function is non-bonded function
Okay.
and it is 1.
Okay. Yeah.
So 1 stands for the type of potential model that we are using.
Okay.
So here we will be using 1261 potential, that is a Lennard-Jones plus Coulombic potential.
Okay.
There are other potential model as well, so we have to change it accordingly.
Okay. So 1 will refers to Lennard-Jones.
Yeah, 1 will refer to Lennard-Jones.
Okay. And that second one?
Second one is the combination rule. In
Okay.
Lennard-Jones potential, we have sigma and epsilon, right?
Okay.
And the combination rule 3 is if the sigma, if epsilon AB is a geometric mean of epsilon alpha and
So
alpha.
which means that combination rule is if you have different types of atoms.
Yes, if you have
If you have
different-
single atom like argon, then it doesn't matter.
No,
because
it doesn't
all
matter.
atoms have the same sigma.
Exactly.
So there is nothing to do.
Yeah.
Okay. And what is the next one?
The
Pairs?
next one is generate pairs.
Okay.
That will. These are not used in case of a monoatomic molecule, but these are
Okay.
used in case of polyatomic molecule. When we come to water and methanol and other complicated molecule, we'll have to use generate pairs.
Okay.
It will generate pair of interactions.
Okay.
And then we have atom types. In atom types, we have to define
And what are those other 2 lines? Fudge? Something?
fudge LJ and fudge QQ.
Yeah.
These are not used for argon atom. These are
Okay.
used for triatomic and polyatomic molecules.
Okay. Okay.
Then we have atom types. In
Okay.
atom types, we have to define the name of the atom. Like here it is argon.
Right.
Then we have to define the mass of argon atom.
Okay.
Then charge is 0. Then there is p type, that is pair types. Then there is sigma and epsilon. Sigma is the distance, so it is in nanometer.
Okay.
And epsilon is the energy, that is the depth of the potential well. It is in kilojoules per mole.
Okay.
This the value of sigma and epsilon and charge will get it from the FF bonded and non-bonded .itp file, which is
Okay.
in the OPLS directory.
Right. So now after that you are including ITP file.
Yeah, after that I'm including an ITP file, argon.itp.
Right.
And then I have to also specify the total number of argon atoms that is being simulated
Okay.
and the residue name.
Okay.
So the residue name that we have already given in the PDB file, we have to use the same residue name, and then we have to give the total number of molecules that are being simulated. Here we are using 567 argon atoms.
Okay,
So we have to specify it.
Okay. So far we have considered PDB file, GRO file and top file, isn't it?
Yeah.
So now what we will do, we will conclude this discussion now, and next time we will start the remaining files. Which are the remaining files now?
The remaining files are ITP file and the MDP file, that is the molecular dynamics parameter file.
Okay. Okay. So we will conclude this lecture here, and the next one we will summarize what we have done so far and then take up the remaining files and then show how to execute the Gromacs package. Thank you.